So you guys know a lot better than I do about some of the irrigation issues. Here you've seen maps like this in the past. They show declines in the Ogallala aquifer. We also have droughts from time to time. This is a drought map from a couple weeks ago. I think February 12 is the date of this map. Seth mentioned the situation about a year ago, and this is February 13, 2018. So we get these droughts from time to time, and they make it very difficult for planting, for growing the crop. So that irrigation is much more important during these times. There's been a lot of progress thus far, thanks to all of you guys producers in this area. Advancements in irrigation systems. Many years ago, this probably was the most common type of irrigation system here, flood irrigation. Then we had the center pivots, but if you look hard, these are the impactor sprinklers sitting on top of the main line, shooting water at 60 psi into the air. And now we have systems like this. This is actually from one of the technology farms that Jonathan from Kansas State is involved with. And they had a program a few months ago, and I had the pleasure to go up there and visit with them. And here they have different types of nozzles, as you can see, a mid-level spray and a LIPA and different types of nozzles side by side. And he's doing a great job there at K Estate. He'll be talking to you. He'll be the person between you and dinner right after me. There's also been advancements in precision irrigation management. And this happens to be the probe by John Deere, but that was just easy to find on the internet. We're not promoting anyone. There are many different products out there. I know some of you guys are working with these probes and finding value in using the probes to fine-tune your irrigation management. Scott mentioned about irrigation uniformity. This is a satellite image that was taken, I think, sometime in summer last year, and you see differences. The red color shows crop biomass, crop vigor. So the lighter shades show areas where crop is not doing good. Here's another area from the same satellite image, so you can compare these three circles with these two circles here and this half a circle here and see how the crop was performing differently. I know we have companies here, some of our sponsors, that provide airborne imagery. You can get the same type of information at a higher resolution from these companies. You can see clearly there are some issues with uniformity, so that's one area where I think we can improve. But other opportunities that exist are perhaps shifting to crops with less water demand, like sorghum or cotton. Also optimizing crop water use through applying some deficit irrigation, maybe changing planting dates or changing seeding rates to see if we can optimize that crop water use, maybe save an inch of water here or there, and extend the life of aquifer a little bit more. So this was the focus of this study. Now, if you want to look at all these different things and do field work, conduct field research, it would be very difficult to have all of these different types of plots with different planting dates and planting densities, and you need several years of data. So you capture different conditions. So it takes a lot of hard work. But we can use computer models. And we can take that information into those computer models. In this case, we use the model which is known as AquaCrop Model. That's the name of the model. It's been developed a long time ago. And this model is especially good for simulating the yield response to water application. It requires a lot of input data. You see all different tabs here: climate, crop, irrigation, field, soil profile, groundwater. And you click on each of these tabs and it opens 20, 30 more windows with a lot of different types of information that you need to provide in there. So that's what Blessing has been working on for a long time. Like any other computer model, it needs to be calibrated and then validated. So you know you have some confidence in the results we get from the model. So what we did for this study, for the response of sorghum, we used field data from two different sites. From the USDA Research Lab at Bushland, right next to Amarillo, which is not too far from here. And also the data that was collected here by Jason Warren, right here at this research station. I think Summit was also involved in that. So we've used information from this very location and Amarillo, and that the data from these two locations have been used for calibration and validation, so we have some confidence in the results. But once the model was calibrated, we looked at 9 strategies. And this calibration validation was an important part because now we have the calibrated validated model. Then if you guys have other questions, other type of scenarios, we can run the model. We don't have to go through this again. So we just came up with these 9 different scenarios, 3 planting dates and 3 planting densities, and we simulated the grain yield for 21 years of data. We got the weather data from Mesonet for that period here, 97 to 2017. We gave that weather information, the rainfall, the temperatures, everything to the model, and then we used the model to simulate the yield. Now the scenarios are here, different strategies. So we had 3 different planting dates, May 25th, June 10th, and June 25th. And then we had 3 different planting densities from low to high, 55,000 to 75,000. So the combination gives you 9 different scenarios and some of the results here. So as far as the model performance, when we do the calibration validation, this is the soil moisture. And the 2 dotted lines you see here are the upper limit and the lower limit. You want to be in between these limits and hopefully not getting too close to the lower limit because that's when you'll stress the plant too much. The black dots are the measurements and the line is what the model gave us. So the model is doing a fairly good job, and soil moisture is very difficult to model with computer models, but the model is doing a fairly good job. There are some exceptions, but for most part, it does a good job. And if you get your soil moisture right, then that impacts the evapotranspiration, the water use, the photosynthesis, a lot of other things. So you can be confident in yield. And this is the performance of the model as far as the yield. So you see the simulated yield. This is what the model predicted. And this is what we actually measured at the 2 locations I mentioned. They're pretty much right on the 1-to-1 line, which means that there's not a whole lot of difference. The model was pretty much right on with what we measured out in the field. Okay, so once we were confident that the model is doing good, then we did the analysis. And here I'm showing only the results for 1 planting density, that's 65,000 seeds per acre, all the years, and the 2 planting dates, the earliest and the latest. I'm not showing the middle because the middle line was right here in the middle. So May 25th and June 25th. And you can see in every single year, the June 25th had a much lower yield. In some years, like this one, they were pretty close, and mostly because the May 25th did not really do good. But in some other years, the difference was really big as far as the planting. If you look at the average values of the grain yield, this is what you would see, all 3 dates and the planting densities. As I mentioned, you planted later and later, you're losing yield, going from probably about 130 something. I have a table that has all the averages down to 110, 112, 113 maybe, and it was different for each of the planting densities. And this was the irrigation requirement. So a somewhat similar pattern. So the later planting date also had a smaller irrigation requirement. And by the way, we let the model automatically irrigate. So the way that the model did it was as soon as about half of the soil moisture was depleted, it applied an irrigation. And we assumed that your well capacity is good enough that you're not going to impose any deficit irrigation. So these are the potential yields that could be reached. If the well capacities are lower and some deficit is applied, then the yields will be lower. And that's the next step for us to model those. We're looking for questions that we could answer with these models. But these are full irrigation capacities. And those are the bar charts for seasonal irrigations. You can see anywhere from close to about 18 inches in this case to maybe about 13 inches here. If you want to look at the effect of each of these treatments separately, here's the planting density. And not a whole lot of difference in irrigation requirements, pretty much the same. And the grain yields were not very different. You gain a few bushels per acre with the higher densities, but for most part they're very close. The main difference was the planting dates, and that was really significant. You can see the impact on seasonal irrigation. Going down from 18 inches to 13 inches, but also a huge impact on grain yield from 136 bushels to 112 bushels. And again, these are the averages for that 21-year period, 97 to 2017, with the actual measured weather data, precipitation information, temperatures, and all those things. So I think I've already covered these conclusions. No significant savings in water, no yield gains, but just changing the planting density, but planting date had a huge impact. As I mentioned, the next step for us is to look at different levels of deficit irrigation if the well capacities are limited, and also breaking out these years into years with different precipitation patterns, late season precipitation, mid-season precipitation, things like that, to see what type of results we get from these models and see if we can use that to optimize irrigation, or if we need to deficit irrigate, what is the best stage to do that deficit irrigation. So these are the sources of funding, provided money for this project. I'd like to acknowledge all of them. And with that, I'm done. I'll be more than happy to take any questions.